finished the last lecture about linear discrete time systems, and we'll look at several things, what happens when you concatenate these systems or connect them in parallel. And at the very end, I'm going to go through a very detailed example of one-star system where we're going to work out pretty much all the steps. So let's look at what happens when we're interconnecting discrete time linear systems. There are two basic ways how you can connect two systems. One is you can put them in series, and the other one you can put them in parallel. If you have a parallel connection, this is what you're doing. You have your input, and you lead this input into two systems that look like this. This is a system 1, and this is system 2. And then what you do is you take their outputs, and then you sum them together. Now, the question is, how do we treat this system? Well, superposition always holds, right? So, for example, if you were to look at what the output of this is, let's say you have, again, two components. One is going to be due to initial conditions of these two systems, and the other one is going to be due to the inputs. Both of them can be added, through superposition. You would first look at the output of this system due to initial conditions, output of this system due to initial conditions, the overall output is sum of the two. But if I put delta of n here, then what comes output is of this system, h1 of n. And what is the output of this one? H2 of n. So you can see this as equivalent system that has an impulse response, which is the sum of the impulse responses of those two systems. Straightforward superposition applied. The second way how we can connect two systems in series. And in this case, you have system S1 with an impulse response H1 of n. And then you lead the output of this system into the input of the new one, of the second system S2, that has an impulse response H2 of n. Now, let's present delta pulse to this one. If you put delta of n here, what comes as the output of this one? H1 of n. But then H1 of n acts as an input into the H2 of n, so you get that the overall impulse response of this is H1 of n convolved with H2 of n. Okay? Now, I'm here just looking at zero state response. You pretty much know what you should, based on what we covered so far, understand what to do with the zero input response. If there's a zero input response, then you would first calculate the output of this one, right? And then the second system would have its own zero input responses plus the convolution of whatever comes as a zero input output of this one convolved with an impulse response of the second system. So there's a little bit of work to do, but then it's a relatively simple one. So let's look at the third thing here, the response of discrete time system to everlasting exponential. Now we've seen that everlasting exponential in a time domain has in a continuous time systems has a special role. It's kind of the function that when you feed that function into the system, it comes back. It comes back because just modified in amplitude and phase. Similar to that, we have here a function, x of n, that is z to the n, which is a generalization of the exponential function. This z in a special case can be e, right? But in discrete systems, z can be any number, complex or real. And let's take a look at what happens when I feed this input to a discrete time system. So I have a discrete time system here that has comes with a certain impulse response, and then I'm putting here x of n, and I'm getting output y of n. What we've known from what we have covered so far is that y of n has to be x of n convolved with h of n. Right? That's our general understanding for a zero state output. Right? If you have zero state output, then your output is a convolution of whatever comes as an input plus the impulse response of the system. So let's substitute this in here and see where it leads us. So this becomes sum. I'm writing now convolution. M goes from minus infinity to plus infinity. H of m, x of n minus m. Right? This is the statement of the convolution. Well, I can substitute now what x of n is here, and I get this is sum when m goes from minus infinity to plus infinity, h of m times z to n minus m. You can see that the summation is over m, right? So this z to the n can be taken out of the summation. It's not affected by the summation itself. So I can rewrite now y of n as z to the n, sum when m goes from minus infinity to plus infinity, h of m z to the minus m. Okay? Now, in every particular case, this z is some complex number. Let's say x plus jy, or I can say r e to the j theta, right? Some particular number. This h are also numbers. This is a impulse response. So what does the impulse response look like? It's a whole bunch of numbers, right? It's just a particular impulse response. But for any given z, this would also be a single number. It does not depend on n. You see that? That for y of n is going to be z to the n, which I can say that this is x of n, yx of n, because x of n is z to the n. And then this number here, which I'm going to call h of z. Let me just make sure this is a single number at any given z. Okay? So this should resonate. This is familiar to us. So this function, z to the n, when it comes to discrete time systems, is a special function. This function you feed in, you get the same function out, albeit it is scaled by some complex number. It is multiplied by some complex number. This h of z is going to have its magnitude and phase. So I can write this y of n as z of n, z to the n, times the magnitude of h of z, e to the j angle h of z. So what happens is when this function z to the n is special, in a sense that when you present this function to the discrete type system, you get the same function back, just scaled by some magnitude and changed by some phase. So this function h of z, or this number h of z, is called transfer function. And one way how we can define it, it's the ratio of the output to the input when the input is x of n equals z to the n. Right? So that's one way of how we can define this one. Now, just like in the case of a continuous time system, there's a way how we can calculate this h of z directly by knowing the difference equation of a given system. So let's review that. Consider, so let me just put that here. H of z may be calculated, or determined, I should say, directly from the difference equation. Of the discrete time system. So consider a difference equation that we write as Q of E applied to the y of n is equal to P of E operating on x of n. These Q of E and P of E are polynomials that are functional polynomials, right? They're operator polynomials. They just operate on the output and input to produce this difference equation. Now, let's take a look at, let's assume, let x of n equal to z to the n. So we're now looking at a general case of the difference equation subject to my input being x of n equal to the z of n. So let's work now on left-hand side. So Q of E applied to the y of n is going to be Q of E, but I know what y of n is going to be. Y of n is going to be the same sequence x of n, but just scaled by some complex number, h of z, right? That is what I have here and here as well. So now instead of y of n, I can write it as h of z times z to the n. But now guess what? This h of z is a constant number. It can go outside of this operator. And then this operator just works on z to the n. So this is Q of E, h of z. And then I have Q of E operating on z to the n. But what is Q of E when it operates on z to the n? Remember, Q of E was e to the n plus a1, e to the n minus 1, plus and so on, plus a n. Now I need to have this operate on z to the n, right? So I can write this as z to the n plus n plus a1 z to the n plus n minus 1 and plus on plus a to the n z to the n. If I take z to the n as a common, then you can see that this is really Q of z, where I have substituted instead of e, I have z of times z of n. Now this is different. Remember, this is now times. This Q of z is again a simple number. It's just a single number. Q of e is an operator, right? You cannot say cancel this. It just says you have to execute these essentially delays or derivatives, right? But once you do them, you realize that in the special case where this is z to the n, this wouldn't work in any other case. It works for this special function. Then you realize that Q of e operating on z of n is essentially this number, Q of z, multiplying the z to the n. So we have a final result here that Q of e operating on y of n is going to be h of z times Q of z times z to the n. All right, so this is our left-hand side. Let's take a look at the right-hand side. Right-hand side we have P of E operating on x of n. Well, this is P of E times operating, z to the n. Why z to the n? Because x of n is z to the n. And just like we did in the previous case, where we looked at what happens when Q of E operated on Z to the n, here we discover that this is equal to P of Z times Z to the n. Now, making the left-hand side and the right-hand side equal, you end up with H of Z times Q of Z times Z to the n has to be equal to P of Z times Z to the n. And then when you cancel Z to the n, you get that H of Z has to be equal to P of Z over Q of Z. So this is evaluation of transfer function directly from system difference equation. Okay, so this is a direct way. So you don't have to kind of rely on this summation here. You can actually evaluate this H of Z directly from the difference equation itself. Now, what you should, and I don't know if I mentioned that when we talked about continuous systems, but remember we know how to do impulse responses. There's no secret there. But everybody would admit it's a little bit cumbersome, right? It takes some time, right? You need to be relaxed, and then you cannot do it in like 30 seconds. You have to say, okay, I'm going to budget 15 minutes, make sure that I do it right. Well, look at this. H of Z can be determined very easily, right? H of Z is trivial. P of Z over Q of Z. It's coming as an inspection from difference equation. Similarly for H of S, remember this was P of S over Q of S. This is now for continuous time system. This is discrete time system, and this is for continuous time system. So both in the continuous time system case and discrete time system case, transfer function is trivial. It comes right out of the difference or differential equation. If there were a way how you can actually determine H of n and H of t straight from these transfer functions, then you are actually given yet another way how you determine impulse response. What I'm saying here is maybe there's another way for determining impulse response, and this is essentially going around about. You determine first the transfer function, and then we go and determine impulse response. And I'm sure somewhere in your schooling you've done it. This would be called inverse Laplace transform, and this would be called inverse Z transform, right? It might seem that this would give you some benefits, and in certain cases it does give you benefits, but what you essentially end up doing are the same very calculations that we do when we do H of n and H of t directly. So you cannot really trick the nature. It's sometimes you can do it one way or the other, but just be aware that there is a way how you can determine your impulse responses directly from H of Z and H of S. Okay, so now we have all the pieces. Let's look at the total response. Of linear, time invariant, discrete system. So we have system S, for which we know an impulse response H of n, and you have this system excited with an input X of n, and you know that at the output there will be an output that we denote as Y of n. Based on what we covered so far, you know that Y of n is going to have two components. One is going to be Y0 input of n, which is essentially the a response of the system to initial conditions. And the other one is going to be y zero state event, which is going to be the output of the system that is forced by this input presented at the input end. Now, what we also know is that this part here is going to consist of the characteristic modes. So J is going to be 1 through n, Cj, gamma j to the n. These are your natural modes. And we also know that this zero state one is going to be whatever is at the input convolved with an impulse response of the system. And that's how we can, I guess, let me just put here, convolution of the input and impulse response. Okay, so the question is now, this is actually the end of theory. This is how far you can take it in the theory, or at least in this section of the theory. We kind of cover how you do this, we cover how you do that, and then at this point we just need to put it all together. And what I'll do is I'm going to walk through a complete example, kind of trying to put steps. I always like putting step 1, step 2, step 3, so that you get some sort of algorithm that is repeatable. Because a lot of these things that we are doing here are not very hard, but they can become messy if you're not organized, and you probably experienced it. So it benefits you if you can kind of organize yourself and say, I need to do this and in this particular order. So let's take a look at an example, and then make sure that you understand every piece of this example. It's essentially going to be doing what I indicated in this equation over there. So example, we have a system given by the following difference equation. U y of n plus 2 minus 0.6 y of n plus 1 minus 0.16 y of n is equal to 5x of n plus 2. And I'm going to start here because I'm probably going to be referring to this equation later. I have also initial conditions y of minus 1 is equal to 0, and y of minus 2 is equal to 25 over 4. Why do I need initial conditions? I will need them to eliminate these constants here in the natural modes. And then I have also input x of n, which is given as 4 to the minus n u. Are there questions? Is there a question, or go ahead?
Can you repeat it again? Why you need the initial condition?
Yeah.
Because you need the response of the.
Yeah. Remember how the systems respond. Based on the analysis we did, we said if the system has an energy, it will always ring using its natural modes. But there's infinitely many ways how the energy can be given to the system at time t n equals 0, right? It may be barely, moved. It may be, at many different states. What this tells us is whatever was the state, it's going to be responding as a bunch of superposition of the natural modes. But how many of these natural modes? What is the mixture of these natural modes? You have to have an anchor point to determine what the mixture is. And these initial conditions serve as that anchor point. right? If you think about the system going through these, you know, by saying, okay, you have to be here at n equals 0, and you have to be here at n equal 1, that kind of determines uniquely what these constants need to be. Out of the space of infinitely many possibilities, you kind of narrow it down.
Okay, another question actually, Professor. With that one, some of the example tell about you need to do that recursively. What does it mean actually?
Okay. Recursively means this, and in principle, you know, you can solve any discrete time problem that way. If I want to do recursively, right? I think there's maybe one or two. You will do this. Y of n plus 2 is going to be equal to 0.6 y of n plus 1 plus 0.16 y of n, and plus 5 x of n plus 2.
Yeah.
Okay?
Okay.
And then you say, okay, well, let me start evaluating. Let's say n is equal to 0, and 1,
Yeah.
so. And then what you will end up with the output. Always. Right? And that's a kind of good thing about discrete systems. They're not as complicated as continuous time, because in continuous time you end up solving differential equations.
Yes.
And they can be solved numerically, but that's not what we're after. But remember, solving these problems is just a part of the puzzle, right? We're not in a world as engineers to solve token problems. You're there to design something. So if you don't like this output and you just obtain it doing recursively, you're kind of stuck with it, right? You don't like it for a particular reason, and usually this is in control systems, so it goes out of bounds or there's something to it.
So it means.
So what you need to have an insight. Why is this happening? And by doing evaluation recursively, you're not going to get this insight. But by doing it, as we say here, decomposing components, then you can say, oh, okay, it's because this, because of that, because my input is not bounded, my output, my poles and zeros are in given places, and so on. So then you know what to do. So, you know, as I say, recursively you can always do it. And my suggestion to you guys is do it, you know, at least for your homework problems, or if you have time, even on the test, do a couple of samples at the end and test. If you're going to be, I'm not going to ask you to do this. I'm probably going to ask you to do this, right? But there's nothing that prevents you from using this to test what you obtain, right? Test first couple of samples and then see if they agree. Then you know that you've done this correct.
It's going to have the same pattern,
Yeah,
like.
it has to have. I mean, however you solve it, it has to have one solution, right?
Right.
And you can, with this one, you can test what you obtain here as a general solution. Go ahead.
So that was my question.
Yeah.
The second question that you asked, that's the question. And the other one is, how do we control the poles and zeros? It's not in our control.
It is. It is. There is something called feedback. There are controllers that you put in there. You know, the first thing that I talked about, connecting in series and parallel, that's when you do this control. For example, when you convolve one impulse response with the other response, you end up with aggregate response that may have different locations of poles and zeros. So what you end up doing is you're shifting them around. Just since you asked, let me just put the basic diagram here. And I'm sure you've seen this. Let's say you have your system here that has a difference equation with P of E and Q of E, right? And let's do this. This is the output. I'm gonna feed this through another system like this, right? Let's call this G, and let's call this H. So H will have P, Q, R of E, S of E. You see what I'm drawing? I'm connecting. This is the system, original system, and then I'm taking the output of the system and designing the system H to get now this big system end to end. Right? So in basic control theory, you learn that the output, overall output of this, let me call this GS of Z, is going to be G of Z 1 plus G of Z times H of Z. In other words, when you put the polynomials, this is P of Z over Q of Z 1 plus P of Z Q of Z times R of Z S of Z. Right, and when you multiply this, but let's say by Q of Z S of Z, so this becomes P of Z times S of Z P of Z times R of Z plus Q of Z S of Z, right? So what you end up with is a system, overall system, GS, that has a completely different polynomials up and down, which means that by inserting this here, I've changed the difference equation for the whole thing. And by doing that, now you have different natural modes, different impulse responses, and this is how we play. And to be able to play with this, you actually have to understand you have to have analytical tools that give you insight in the behavior of the system, not just the description, right?
Sir, is there any software that in which we can just simulate all these things and see the result?
Yeah, and what is that software?
MATLAB?
MATLAB, right. MATLAB is actually, this is where MATLAB started. MATLAB is, because what you find out is, this is all notation for this. The best way, and I hope that we're going to get to that in this course, these differential and difference equations lead themselves to another formulation that's called space state formulation, where you turn the, let's say, n-order differential equation into first order differential equation, but matrices of n×1 matrices. And what happens is, this is what we call space state form, and that's where MATLAB started. Many people think MATLAB stands for mathematics, math stands for matrices. And the whole, space state model and everything is kind of, so look it up. It's in every version of MATLAB.
So which tool? Which toolbox?
Toolbox. There's a control system toolbox that just does this, but in a general toolbox, many of these tools are already there. Yeah. All right. So let's go back to our not following what they always told me. I'm going to erase this, the last thing I wrote. So if you're copying,
yes.
give you a second, because I want to use the board to start the problem. But linear system theory has, it's kind of like a central thing. And then you have all of these offsprings, right? The biggest offspring is a control system here. And what does this one deal with? You're trying to design a system, you're trying to modify the properties of the system to conform to some specifications that you are trying to achieve. It needs to have a certain stability, certain gains, certain responses, whether it's slow, fast, whatever the case may be. So the big offspring is control system theory. Then the next one is DSP, right? DSP is actually also system design, but the purpose of the DSP design is relationship with X of n and Y of n. Your object is to design S to do something with X of n to produce Y of n. A good example would be noise elimination, identification of the characteristics, voice recognition, whatever, right? Then you have a communications, right? Communications also uses all of these, but here is usually some received signal that picked up all sorts of, pardon my expression, junk as it propagated through the communication channel, and now you need to design a system here to clean it up, right? And that system consists of filters, it may have encoders, decoders, all sorts of things, multiple antenna, combining and so on. So there are all of these really practical applications that kind of run the world around us that require that you have this core or understanding of linear system theory. All right, so let's solve this particular example. So when you give a problem like this, the first step is to look at zero input response. In other words, for the time being, we're going to assume that there is no input to the system, and we're going to just calculate what happens as the output as a result of these initial conditions. And we know how we do that. We first form a characteristic equation, Q of gamma. Essentially, this becomes a polynomial, gamma squared minus 0.6, gamma minus 0.16 has to be equal to 0. And here we solve for gamma 1 as minus 0.2, and gamma 2 has to be 0.8. From these two, you can form the zero input of z, your zero input, not z of x, sorry. Your zero input response is minus 0.2, constants, right? So it's going to be C1 times minus 0.2 to the n plus C2, 0.8 to the n. So that's a general form of this system of the zero input response. Step 2. Determine impulse response. Here we start by saying e squared minus 0.6 minus 0.16. This is operator form. Y of n is equal to e squared x of n. The reason why I suggest you rewrite it here is because you want to understand what is the order of polynomial here, what is the order of polynomial here, and identify coefficients. Because we have the result from the last class that our impulse response is going to be Pn over An times delta of n and plus Yc of n times u of n. Okay? That's the result that we obtained the last time. This one tells us when I have impulses in my output. In other words, there's a direct coupling between input and output. And this is the part of the impulse response that corresponds to natural modes. Remember, after the impulse is absorbed, at n equal 1, 2, and that happens at n equals 0, for the consecutive steps, n equal 1, 2, 3, the system behaves as it was delivered some energy at n equals 0, and then after that it's a zero input response, right? So therefore you have these natural responses that are after this potentially initial pulse. So we know that in this case, Bn is equal to 0, right? Therefore, the first part of the impulse response is non-existent, and our h of n has to be equal to k1 minus 0.2 n plus k2 0.8 to the power of n. Now, how do we determine K1 and K2? We have to determine K1 and K2 by a recursive evaluation of this equation for x equal to delta of n. We need to create initial conditions for impulse response. So to determine K1 and K2, assume, let's put that here. We assume age of n, x of n is equal to delta of n. And then really we use this equation here, or the one that I just erased, to determine what the values of your impulse response need to be 2 consecutive times. I don't need more than 2 because I have 2, the order of my difference equation is 2, and I have 2 constants that I need to determine.
Excuse me, sir. Before assuming x of n equal to del n, what did you thought? Why did you took only del n? Why not x of n is equal to u of n or 0?
You can.
What was at the back of the mind?
What is age of n?
Impulse response. So,
So what is the input that I need to put?
impulse? Okay.
Impulse, right? This is not the step response, it's impulse response. So that's why I'm putting delta on it. Now the question is, I know that impulse response in this case consists only of natural modes, but even if it doesn't consist, even if this term was there, you're still going to have a couple of constants, or n constants that you need to determine. And you determine these constants by evaluating your impulse response at n different points. Now, okay, so let me do that here. So if I take this equation here and I rearrange it just like I had it a little time ago, meaning that everything except the highest order term on the left hand side goes to the right hand side, I get that y of n plus 2 is going to be equal to 0.6 y of n plus 1 plus 0.16 y of n, and plus 5 x of n plus 2. And really, most of the time what we do is we shift because depending on where your initial conditions are given, if they're given, like in this case, for n equal minus 1 and minus 2, then you shift everything by whatever is the highest order here. So this is 0.6 y of n minus 1 plus 0.16 y of n minus 2 and plus 5 x of n. And now your equation is ready. So what you do is you say, okay, when n is equal to 0, I have age of 0 equal to, let's see, from here it's going to be 0.6 age of n minus, well, these are the, sorry, let me just do this. Age of n has to be equal to 0.6 y age of n minus 1 plus 0.16 age of n minus 2 and plus 5 delta of n, right? So now, when n is equal to 0, what is age of 0? If you look at all of these, since this is an impulse response, before 0, age has to be equal to 0, right? So this is 0, and then at 0, this is 1. So the age of 0 is going to be equal to 5. And then when n is equal to 1, age of 1 becomes equal to 0.66 times age of 0, which is going to be 6 times 5.
0.3.
3, right?
0.3. Sorry, 3.
Yeah, 3. And then the rest of it is going to be 0. So just 0.6 times 5, which is 3. Now, when I know that, then I look at my general form, and I also know from general form of the impulse response. Age of 0 is going to be k1 plus k2, and that has to be equal to 5. And age of 1 is going to be minus 0.2 k1 plus 0.8 k2, and this has to be equal to 3. And when you solve k1 and k2 from here, I'm not going to bore you with solving system equations, but k1 ends up being 1 and k2 ends up being 4. So you end up with your impulse response, age of n, which is k1, which is 1 times, so 0.2 to the power of n, plus 4 times 0.8 to the power of n, and then everything times u of n. Okay, so this is your impulse response. Okay? So now we have our zero input response, or at least we have a form of the zero input response that is here. And then we have our impulse response. So now we need to determine our zero state response. So this is step 3. Zero state. Zero state response. And we know that this one is zero state of n, will be determined as x of n convolved with age of n. So in this particular, in general, this is sum when n goes from minus infinity to plus infinity, x of n, age of n minus n. So, if I substitute here, y of n is equal to sum, m goes from minus infinity to plus infinity. What is my x of n? X of n is this thing here, but I just need to substitute m for n. And then I need to convolve this with my obtained impulse response here, which is minus 0.2 n minus n plus 4 times 0.8 n minus n, everything u n minus n. And
Times. That's times.
times, correct. No convolution, times. So note how I'm doing this. I'm really trying to follow the formalism here, trying to formally kind of replace everything as it states in these formulas, which means I'm not dropping u's there, you know, and I'm kind of making sure that I subtract everything appropriate. Now, at this point is where your first simplification has to take place. And the simplification comes from realizing what these u functions are going to cut out. So this summation here simplifies. And it says this is sum when n goes. Now this u of m says you don't need to sum anything before 0. Why? Because when m is smaller than 0, this u will make it 0. So I sum from 0 here. Now what does this one say? You don't sum anything where m is larger than n. Why? When m is larger than n, then n minus m becomes negative, and u of negative number becomes 0. So I'm summing m equals 0 to n, and then I can get rid of these u's, because I already took care of them. In the rest of the interval, they are equal to 1. So they're just equivalent to multiplication by 1. So you end up with 4 to the minus n that multiplies minus 0.2 to n minus n, and then plus 4, 0.8 to n minus n. So that's what I need to sum. And there is really no wisdom here. It's just you have to be patient, and you have to be meticulous. You cannot write nicely. You have to write nicely too, because otherwise you'll make mistakes copying from one row to the other. So let's see if I can replicate what I have in my notebook here on the board. First thing you realize that this is minus 0.2 to the n divided by minus 0.2 to the n, right? So the to the n does not depend on this m, and it can be taken outside of the summation. So this first one becomes minus 0.2 to the power of n times sum, when n goes from 0 to n, 4 times, let me say something like this, minus 0.8 to the power of minus n. See what I did? It's 4 to the minus n, minus 0.2 to the minus n. So 4 times minus 0.2 is minus 0.8 to the power of minus n. And then the last term becomes 4 times 0.8 to the power of n, and sum when n goes from 0 to n. 4 times 0.8 is 3.2 to the minus n. Okay? Now, this see, I made a mistake here in the notebook, right? Negative sign where? Seems like in the notes, 1/4 is missing, right?
Looks good on the board.
Hmm?
Looks good on the board.
Looks good on the board. That's so far so good on the board, right?
Yeah.
Let's see what we end up with. So we have two summations here. The first one, we have minus 0.2 to the n. And then this one here, we know how to sum this, right? This is essentially, let me rewrite it so that it fits our previous formula. So it's minus 0.2 to the n. Sum when m goes from 0 to n. And then I'm going to have 1 over minus 0.8 to the n, right? Because we learned how to sum the geometric progression. And then here, the second one becomes 4 times 0.8 to the n. And then sum when n goes from 0 to n, 1 over 3.2 to the n. So we are using this result, sum n, which is sum q to the n, where n goes from 0 to n, is equal 1 minus q to the n plus 1 over 1 minus q. Remember I gave you that expression last time. So using this, we get that y of n is going to be equal minus 0.2 to the power of n. And then I have 1 minus 1 over 0.8 to the power of n plus 1 divided by 1 minus, which is going to be 1 plus 0.8. And then the second one becomes 4 times 0.8 to the power of n. And then here 1 minus 1 over 3.2 to the power of n plus 1 divided by 1 minus 1 over 3.2. Okay? Let me see if I can.
1 plus 1 over 0.8. The first.
Yeah. So what I did here is,
U of n, right?
hmm?
U of n for all that?
Yeah, at the very end, right? At the very end, we're just gonna append so that I don't have to drag it. So now at this point, you have to tidy this up, right? And it's not easy without a calculator, but you can see that you're gonna have terms that are 0.2 terms, then you're gonna have 0.8 terms, and you're gonna have 4 terms, 4 coming from here. 0.8 times this one, right? So after some dots, right, I have the following result. Let me, because I think what I did is I copied this from the book. So it's probably correct. But let me, actually, we have time, so let me go through these calculations. So this first one, it becomes 0.2 to the end. And then we have 1 plus 0.8. So if I multiply top and bottom by 0.8, I have 0.8 divided by 1 point, so upstairs 0.8 and downstairs 1.8. That's the first term here. For this one, this is minus 0.2 to the end. And then I have 1 over 1 plus 1 over 0.8. So if you multiply top and bottom, you get 0. Upstairs and 1.8 downstairs. Then you have minus. Now I have 0.2 to the end and minus 1 over 0.8. So I can say that this is, let me take minus 1 over 0.8 outside, and then I have 0.2 over 0.8 to the end, and then I have that multiplied by 0.8 over 1.8. Did you follow this one?
Yes, sir.
Yeah, so that's the second piece here. The first piece here is 4 times 0.8 to the end. And then I multiply top and bottom by 3.2, so I have 3.2 divided by 3.2 minus 1, which is going to be 2.2. So there's 2.2 here. And then the last one here becomes minus 1 over 3.2,
4 over 3.
and then 4 here. And then I have 0.8 over 3.2 to the end. And then I have 3.2 over 2.2. Right? That's the fourth term. Right, this 4 coming up front, then this 3.2 coming from this 3.2 here to make this n. Then I have 0.8 divided by 3.2, everything to the power of n. And at the end I have to take care of this, so I'm multiplying 3.2 top and bottom, and I get 3.2 upstairs, 2.2 downstairs. And you can see that there are terms here, let's say minus 0.2. Let's say, where is minus 0.2? I have this term only, right? So it's 0.8 over 1.8, which is 0.444. Is it true? Sounds right. To the end, right? Then I have the second one is 0.8. So let's see, plus 0.8 to the end. Where is my 0.8 term? Just this guy here. So this becomes 4 times 3.2 over 2.2. And this is slightly bigger than 4. 3/2 of the 4. So it should be between, it's close to 6. So this is 581. And then plus, now I have here, this is 4 to the end. And this is 4 to the minus n. But it's interesting, how is this? No, this is 1 over 4, and both of them are 1 over 4, right? So this is 4 to the minus n. And then I just need to make sure that I add all of these correctly. So if I'm to trust what I have here, this ends up being times minus 126. Right? So that's these two terms. This is 4 to the minus n, 4 to the minus n. You can see both of them are minus, right? Actually, the first one is plus, so it becomes 4 over 2.2, it's about 2, and then you have minus 2, and then this is, what makes it, around 1. So I double check the math, but I'm thinking it's correct, right? So that's how, when you get the known, you have a known result. If you look at the derivations, this 4 is missing in the in-between steps, but the result is, I believe, correct. So that's our zero state response. Zero state response, and then we need to put all of this together. So total response, that's in step 4. Total response, y t of n is going to be our y0 input of n plus y0 state of n. And this becomes C1 times minus 0.2 to the n plus C2, 0.8 to the n, and plus this thing here. So this is minus 126, 4 to the minus n, plus 581 times 0.8 to the n, and then plus or plus 0.444 times minus 0.2 to the n. So that's our total response. And then we have initial conditions, right? Applying initial conditions. We have that y total at minus 1, which according to initial conditions has to be equal to 0. Now if I substitute minus 1 here, sorry, this is u of n. We have to make sure we understand that one. We get that this is C1 times minus 2 to the minus 1 plus C2, 0.8 to the minus 1. That has to be equal to 0. And then if I apply y total at 0, which is 25 over 4, I end up at C1 plus C2 plus, now when I substitute 0, all of these are now contributing. So you have plus minus 126 plus 0.444 and plus 581. And from here, you can solve for C1 is equal to 0.2, and then C2 is equal to 0.8. Just easy way, easy 2x2 system. So now, once you know these conditions C1 and C2, then you get the total response as 0.2 times 0.2 to the power of n plus 0.8 times 0.8 to the power of n minus 126 4 to the minus n plus 0.444 minus 2, 0.2 to the n, and then plus the last one is going to be 581 times 0.8 to the n. And this is valid for n greater than 0. Okay? So that's the whole problem. You see, there's a lot of, there's 4 major steps, but you got to be careful because there are a lot of places where you can make mistakes. So that means you need to practice this stuff a little bit more than some other. Let me summarize what the steps are so that we have them all in one place. So here's a summary. Step 1, determine 4 of 0 input response. Now, I don't know if you noticed, but this is an important point here. At this point, all you can do is determine the form of a 0 input response. Your initial conditions are given for, your initial conditions are given taking into account, you know, your input function a lot of times. Therefore, you cannot determine the coefficients for C1 and C2 all the way until the very end, like I did here. Because, so at this point, you just determine the form. So I have a comment here, leave the constant. You're going to eliminate them at the very last step. Step 2 is determine impulse response. And remember, this step has a sub-step in which you determine the initial conditions for the impulse response by doing recursive evaluation of the difference equation for input x of n equal to delta of n. So that's the second step. The third step is determine 0 state response to the input. This is a straightforward step, but usually the most laborious, right? Here is where you're hit with the convolution. Here's where you need to evaluate convolution of some sort, because you have x of n that you have to convolve with an impulse response that you determine in step 2. And then step 4 is the final step. Use initial conditions to eliminate constants in 0 input response. So that's the process. Let me give you a homework assignment, some problems with exercise, all of this stuff.
No, sir.
No, sir.
Say again?
No.
Yes.
Don't do this.
Sir, we are already lagging a lot.
What happened?
They like homework.
There's just a couple of problems, right? So 3, 8, 10,
I want to cry, sir.
11, 12, 13, 3, 8, 20,
Alice will.
28, and then 3, 8, 2, 3, 4, and 8. So these four use four-step approach. That I just count. Oh, 3, 9, sorry.
Somewhere there's a 3, 9.
Here. Sorry. And then whatever you encounter as a problem, just bring it next time and let's go through that. I don't guarantee that I'll solve it, but I'll give it a try.
So for the midterm is on next Thursday?
The midterm is next Thursday.
And it's gonna include all the way up to
Up to
29?
this point. Up to this point. Yeah. So you have a week, right? You have actually more than a week. You have 10 days.
So we only have one more class.
You have one more class that's just a review class, no new material. We're just going to be solving problems. And then you have a week from that class. So there's plenty of time.
For determining the constants K1 and K2, I thought we did something where we used the first derivative and set it equal to 0.
The question here is determining constants K1 and K2.
Right.
K1 and K2 came in here, right?
Right.
K1 and K2 were the constants that are part of the impulse response. Remember, the impulse response has the following form. H of n is equal to Bn over An. Just be patient a little bit. Let's answer the question. So Bn over An times delta of n, and then plus this Yc of n times U of n. This is trivial. You determine this part straight from the two polynomials. Now for Yc of n, you know that Yc of n are your natural responses. So it's going to have some kj gamma j to the n, where j goes from 1 to n. Right? You're going to have n terms here. And the question is how you determine these guys. Now you determine by creating your initial conditions, and you can create the initial conditions by taking the original difference equation and substituting x of n equal delta n, and just evaluate it a few times.
Right.
Because your output is going to be h of n, so you're going to have h of 0, h of 1, h of 2, right? And however many you need to solve for this case. And then once you solve for this case, you have the, so there's a mini initial condition problem inside the step 3.
But in the homeworks, we had one where we just used the derivative and then said that if it was a second order, the first one would be 0, would be equal to 0, would be equal to 1.
You're mixing continuous and discrete.
Was that continuous?
Yeah, in continuous, remember, in continuous we had that our impulse response, h of t, had now help me here, it was a0 times delta of t plus p of d operating yc of t times u of t, right? That was our impulse response in the case of continuous system, and this yc of t was was a zero input response of the companion system, and the companion system is the system that has the same q but p equal to 1.
So we can't do that for this.
No, that's why they differ, right? And a lot of books, that's why I like the approach in these books. A lot of books teach them in parallel, and this is the major confusion here. So that's why I kept them separate. You see, the thinking is the same, but the approaches for these two are completely different, right? We didn't define a companion system because it's much simpler in the case of discrete. In the case of discrete, you have these two parts, and then you create initial conditions. I mean, it's kind of similar if you dig it, you know, there's complete analogy, but it's not as straightforward. So that's why I keep them separate. And I suggest you kind of, for right now, keep them separate.
Sorry, Professor, it should be 3828.
3828.
Yeah, it's not 39.
Oh, here?
Yeah.
I have a real-time spell checking. Anything else? Okay, so go ahead, you know, study some before Thursday, and let's go over some problems on Thursday. What I'll do is, I'll try to do this as I did last time. I'll solve some problems and I'll put them on the web, but we don't need to go over them. Just bring yours already, that's where you have more problems.